Alrighty, friends. Reminders. Python training, either do it because you don't know Python, and then send me an email by next Friday. So I know that since it's not a grade and I'm not pushing on you, there's like probably no pressure. But just do a little bit all the time. All right, just a little bit every day, and you'll get there. It's not that long. This is really not bad. I don't know, then I wrote why here, and okay, now I remember. So you don't really need to learn how to code anymore, right? What I want you to do is to learn how to read code and understand it when you see it, to understand what is happening. But this class is not about teaching you to be a coder from scratch. In fact, there's an assignment coming up where I will ask you to implement a new method that we're just going to talk about a little bit. It's kind of a twist on Newton's method, except the function isn't differentiable. Good morning. Oh, sorry, head hanging low. Just thought I'd harass my friend Lavina. So I'm going to ask you to do an implementation of something, but it's essentially going to be take the Newton's code and hack it into this new thing, and we'll work together. We'll make you're not going to be left alone. There's lots of people. We'll probably have a work day in here because work days are kind of chill and good. Oh, I see all the nods. So we will definitely have a work day in here. And my goal is to have this assignment out by Friday, so I hope to post it on our class page on Friday. And if I do so, then Monday will be a work day. Come on in. Probably start it, let's be honest, probably start it on Monday. But if you started early, that would be great, especially if you're stressed about coding. And then please do read the chapter 1 stuff in that book that I recommended. I'm going to talk about it all in a very different way, and you're going to get a totally full perspective if you read what they are saying. So is there anything you all want to talk about, bureaucracy-wise or content-wise? We're all good? Okay, all right, cool. So that's the news for today, and I've already lost my eraser. It's on the floor. It is? Oh, thanks. That's good stuff. So last night I got really stoked about coding. And I was hanging out we're taking care of a rabbit. In fact, we're actually taking care of Nick Michael Bust's. We won't go into all of that, but Nick Michael Bust rabbit, because he was a really good friend of mine. And all that, I wasn't even sure. Man, all that stuff happened. You know what I'm talking about, right? Okay. I'll just let you look that up. Yeah. He is no longer at Regis for some reasons. So, he was one of my closest friends. And then he kind of fell away. His first son, this is weird, this is what I'm putting on here. And his son died a couple of years back at like 10 days old. And ever since then, he just died in a way to all the people who loved him. And he just kind of became really distant. And then that shit happened. And it was like, oh my God. It was just rough at our house. Luckily it was 3 weeks before the semester because I wouldn't have been able to be here. But we adopted his pet rabbit, Bugley. And so now we have a rabbit who owns our basement. And we have our 2 pug daughters upstairs who are prey driven. And we keep away from the rabbit. Why was I telling that story? God knows. Maybe I better drink some tea. What's in this tea? All right. So could you either get out, let's open up our notebooks or get a calculator out. You're going to need a computing device just quickly. What I want you to do is probably easier with a calculator, honestly. So if you have a calculator, please pull that out. Because then you can just hit repeat on this. Otherwise, if you use Python, you'll have to keep doing functional composition, which is okay. Is anybody using Python interpreter for this? Or everybody got a calculator? You can do it? Yeah, okay. Or, yeah, you too. You can look at Ava's calculator. That'll be good. So what I'd like you to do is type in a 1. Make sure you're probably in radian mode. I'm not sure this will matter. Yeah, I think it'll matter. Type in 1 and hit sign. So 1, enter, sign, however you do that. And then keep taking sign of this. So do the sign of that again. And I know we did this. That's okay. We did it with cosine, right? Just keep hitting it. What's happening? Sine of sine of sine of sine of sine of sine of 1. What's happening? And I'd like to ask you a deeper question, because this is like anybody can do this, right? We could literally get a squirrel to bang the button over and over again. You wouldn't know what was going on. First off, what's happening? What is this value approaching? 0. Seems like it's going to 0. Let's make sure we all see that. Yeah. Good. Why? Now that's the hard one. What does the sine graph look like? Let me just give you a second. Oh yeah, what'd you say, Neva? Yeah.
Oh, I was making the
Yeah, you're making a sine graph.
The noise.
Cool. All right. Cool. So sine, like so. Yeah. What's this? If that's x, what's that coordinate? Right there. What?
2 pi.
2 pi. Thank you. Okay. Cool. What's the one in the middle? Yeah. Nice. Pi. Pi over 2. Halfway. Thrice pi over 2. 3/4 of the way. Awesome. And so what we're doing is we're entering 1. This is like 1.7, or no, 1.57. I think half a pi is about that. So the 1 is about right here. So there's a 1 actually. And when we enter it, we get out this value here. So that's actually cosine of 1. And then we enter cosine of 1 and find, or shit, sine. Sine is what I'm saying. We put sine here so I remember. That is sine of 1. So then I take that and use it as my argument. Think about how that works. We're basically using this y coordinate now as the x coordinate. So we flip it over the diagonal. I'm literally going to flip it over the diagonal and see what I get. Another way to think of that is that I went up to the curve and then I go over to the diagonal and then I go down to the curve. Now think about it, this thing right here is the sine of 1. And then what I'm going to do is from here I'm going to go to the diagonal horizontally or horizontally, and I'm going to go vertically up to the sine curve. And I'm going to repeat this over and over again. And hopefully, the way I've drawn this, I think, is pretty bad. It's not going to settle down. And I'll show you why I know I've drawn it bad. Because sine, if this is the diagonal, what is the slope of sine at 0? What is the slope of the sine curve right here? It was 1. How'd you get 1?
Because the derivative is cosine.
Yep, exactly. So this is the slope of sine at x equals 0, and that is cosine of x evaluated at x equals 0, and that's good old 1. So the slope of sine right here is 1. That means this line with slope 1 is the tangent line, and my drawing was way off. Because what actually happens is that lives above sine and goes like this. So now let's actually trace this out. So sine of 1 is a little bit left of the maximum, or 1 is. And then I go to the curve, and then I go horizontal to the diagonal, and then down to the curve, over, down, over, down, over, down, over. And what I see is this kind of coursing towards 0. with this process called cobwebbing. And that's kind of what I want to talk about today, more cobwebbing stuff. Because it's a great way to understand what we were doing. And what are we doing? We are looking for fixed point solutions. We're looking for the value that when I enter it and I keep doing the thing over and over again, it doesn't change. So this is an example of fixed point iteration, which we're going to call FPI from here on out. Iteration. And hopefully you did do some of the reading. If not, you will see there's a whole section on this, and it will sync this all in a very strong way. So fixed point iteration means this. I've got some function, and I want to find fixed points of it. Now what that means is that I want to find the x values that when I put them in, the output is exactly the same. i.e. solve, and solving is what we've been doing, f of x equals x. Find the input value that doesn't change, it is fixed when you run it through the function. So one way to do this is we could rewrite this. So we could use bisection or regula falsi, or Newton's method, and I think those are the three we've talked about. But we have to alter this. So we would have to create an equation equal to 0. I would subtract x from both sides. And then just call this is my function I'm seeking the roots of. So seek the roots of this side. So a little bit of alteration turns this fixed point problem into a problem we've been working on, and we can handle. We got the code for it right there. We just have to take our f of x, subtract x off of it, and play. So that's the code that I wrote yesterday, and I think, let's talk just a little bit more about this. Not every function will be in this form. You don't always have an x floating around. So let me pop out a few examples here of some pretty interesting ones. So for example, and let me head this up here, we can convert any solve problem into a fixed point iteration problem. So let's think about how to do that. First off, let's just take a look at a nice simple one here. I've got cosine squared of x, different one. Cosine of pi x equals x squared. Solve for x, find the solutions. One thing you probably want to do anytime you've got a problem like this is get a graph. Highly recommend going to Desmos and plotting this stuff out so you can see what is at hand. So let's actually do a little quick sketch here. This is basically looking for the points in common between y equals x squared. This is one way to view it, probably the easiest. And cosine of pi x. What's the period of cosine of pi x? 2, right? So if you have cosine of ax, its period is 2 pi over that a in front. Because it's speeding up the input. It's multiplying all input by pi, so you get there faster than you would. It compresses the domain. So this is 2, this is 1, and I can go up here. That's clearly 4 right there. But I've got my whole cosine curve occurring in this little window here. So if that's 4, that must be 2, and that must be 1. And so my cosine lives in that weird little box, and it's something like this. I don't like it. I gotta fix him. That's a little better. So this is the thing we're looking for. that point, the x coordinate of this point where they intersect equals our solution. By doing this, I now have a bracket for the solution as well, right? I know that the solution lives between 0 and 1. So the solution lives in this bracket, 1 to 2. So if I need to do any bracketing, like for bisection, or any method that requires bracketing, a regula falsi, false position, then I can use this graph to get that. So this is initial bracket if I want one. But I do know it gives me information about the root, if nothing else. So how do I convert that into, Lou, question?
Is the solution actually in that bracket? It looks like it's in between 0 and 1. At least in your
Oh,
drawing.
thank you. Yes, sorry. Yes, thank you. I looked at the wrong
No, you're-
bracket. Thank you. I appreciate that. I appreciate your furrowed brows always, because I know I'm in trouble. And it's good trouble. It's trouble I need to be in. So thank you. So that's our initial bracket right there. How do I convert this into a fixed point problem? And if a fixed point iteration problem? Well, this is interesting. And this is actually something I never looked at till yesterday, and I got so freaking stoked about it that I was like, you're gonna be stoked about it. I decided you're gonna be stoked about this. So any suggestions? Let me just see what's out there. How could I rewrite this as a problem of the form function of x equals x? Suggestions? Lots, and honestly, there's probably infinitely many answers.
Square root both sides.
Could do a square root of both sides. I gotta be careful to make sure that cosine doesn't go negative, but why would I not have to worry about that?
Is that because your bracket is 0 to 1?
That's actually, yeah, well, let's look what happens to the cosine though of pi x between 0 and 1.
Oh yeah.
It actually goes negative.
But your x squared.
Yeah, so, and the x squared tells me this has to be non-negative on this side, right? So as long as this would be positive, I could do that, Cormac, and take that. That sounds scary, because there's that's the fanciness there. That's too fancy. But it would work. Other things. Do you have something?
I kind of want to divide by x, but then
Yeah.
I'm worried about dividing by 0.
Yeah, it's okay. Because look where we live. We're not going to hit x equals 0, right? Our bracket starts at 0, runs to 1, so we can easily at least start in a place where that makes sense. So I like that. So one route is divide both sides by x. Now you may be starting to see the game. Do you see my razor? Okay, there it is. So route 1. And we're going to try a couple routes. Route 1 is divide by x. So this problem becomes cosine of pi x over x equals x. And now I'm finding the fixed points of this thing. So it turns into that problem. And I can now use cobwebbing. If I have a cobwebbing method that does fixed point iteration, I'm set up. Well, guess what? You're set up. So let's get our notebooks out and go to world class, and hopefully I opened it up. And this is going to be, I'm going to try this thing over here and see how this goes. So there's a new piece of code that should hopefully be in the solving section of content. Is it showing up one that says FIP something? It's a notebook. Yeah, cool, awesome. So please get that opened up into Python notebook, Jupyter notebook. I'm still here. there's some, I also like was having fun, like I put some cool coding stuff in. I want stuff for the folks who are coders that we can like go, oh, that's so pretty. And you probably already know a lot of it, but there's some neat ways to do things that aren't necessarily common. They might be here at Regis. I have no idea what the computer science department does to you. I have a sense. I've heard stories. Pam's still here. Why are you being such a chump? Well, I've already got the notebook opened up here because I wrote it. So there we go. Cool. Let me change the inputs. Thought it was that input there. Yeah. Oh, the sound of this thing coming down. Anybody in here watch Three Stooges? Ever? Yeah, that's Curly. I hear Curly every time I bring that thing down. So this is gonna look a little crooked, but at least it's not blocking your view. So some new things in here that will be helpful at some point for sure. I'm using the SciPy library. So notice, and I've actually tried to do these things in a couple different ways. From this particular library that you just have to know exists, I pulled out this method called fsolve. Fsolve is a numerical equation solver that you can specify the method you want to use, and it can find multiple solutions, and it returns a list of those multiple solutions if they are there. So bringing in fsolve so that we know the true solution, because we're going to talk about error today and how error can change as we iterate. And then I define this routine fixed point. Oh, let's see what else I got here. NumPy is NP. That's a classic. And then here's how you bring in a pi constant from the math package. Bring in just pi. So we define this fixed point iteration here. Let's look at the inputs. Now, everything is required because I don't have equal something in here. So these are all required parameters. The function we're looking for the fixed point of. Where are you going to start looking? What is your initial x value, your rough fixed point? True fixed point is going to come from fsolve. We're going to pass that in. And then just a max number of iterations so we don't run forever. And it's easy to tweak that. So we come in here, we set x originally to the initial value. We don't have any errors here, so I put this in because we might get a division by error, a 0 error, and we just want to catch that if that happens. Now this is cool. So this f, I haven't really talked about it before. This is a formatted string. A string is just text and numbers and all sorts of stuff. And if you put an f, you say print, parenthesis, f double quotes. This tells it that it's going to have variables in here that we need to get the values of. Notice this cool notation. I've got braces around each of these. This is the title of the column. So I'm going to print out my results in a column. And this is the title column right here. This says print a formatted string. In the first thing, I want to print the word iteration. And I want to left align. That less than, that is aligned to the left side of the columns. If I had a greater than sign there, it would be aligned to the right. And I don't know off the top of my head how to do centered. We could just look that up. So it's going to create a 10-space column and move everything to the left underneath it, especially this word. Then we've got a value, the current fixed point approximation. We're going to take our absolute error, which is this value minus the true value that we discern from that routine. And then the error ratio, this is going to be the error of the current, oh, it's me. The error of the current approximation divided by the error of the previous approximation. So we're going to keep track of error ratios. Then we run through here. for I in range, blah, blah, blah. Look, that's exactly the fixed point equation. Your next output is f at the current input. So if you're not used to this in computer land, this looks weird. What happens is you take your current x value, you run it through here into f, and then x changes its value to the output here. So this is really odd if you're not used to coding. But it's just like x new equals f of x old. And it automatically overrides the x. Here's my absolute error. That seems pretty straightforward. That's absolute value. If previous error is not none, then we had some kind of error, and we'll worry about that. See, we've got some error here. Otherwise, oh no, this is actually okay. There is no error. So we'll go ahead and we'll print out the next column, next row in our table. Otherwise, we had an error, and we're going to print out this thing barfed. It doesn't make sense. We had division by 0 or something. And then just update, keep track of the previous error. So that's it. That's a simple routine. Non-coding friends, are you able to follow these? Like, not necessarily produce them, but follow the logic? Is it working? You know, just like kind of looking at the few who haven't had much coding experience. Awesome. So we're going to run a number of experiments together today. As soon as I can find my freaking, well, I'll just use touch screen here. So look at how I defined my f. CS people, do you use lambda notation?
Don't look at me.
No. Okay, cool. Something new. I had a suspicion. So look at this really cool way to define a function. It's called lambda notation. And I'll compare it to the way we would normally do this, which is the way I've actually done it in previous code. But I want to create this function f that takes input x and spits out this value. So this is just f of x equals 3 minus 1/4 x. And the way you use the notation is you say f equals lambda space your input variable colon the output formula. Why is this nice? Well, one thing is it's all in line. It's all on one line like a function would be. Using the define function notation, things get a little sprawled out. It doesn't handle piecewise defined functions well. But if you had something you wanted to just pass a function to, you don't even have to name it. So this is a function that Python understands, and I could pass it into a routine just using this as an argument on a function call. Okay, cool. So then what I do is I create this new version of the function, which is take the original function and subtract off x. We'll talk about, let's see, why would I do that? So let's say my function is f of x is 4x times 1 minus x. To find the fixed point of that, I want to solve f of x minus x equals 0. So what it's doing is it's taking the thing I want to find the fixed point of and converting it into the left side of a root finding problem. Does that make sense? Okay, good. You're gonna have to do that. And then I pick my initial value. Let's actually tweak this to the function Lou gave us. So it should be, gosh, what was it? What the hell was it? What is that function you gave us, Lou?
Cosine of the pi x divided by x.
Cosine of pi x over x is our function. So let's do that. And come in here. Actually, before you do that, let's just run it as it is, if you wouldn't mind. Yeah, because I want to talk about this before we get too exciting. Okay, so run that and then look at the beautiful table at the bottom. Let's think about what just happened in terms of cobwebs. So the function itself was it 3 minus a quarter x? Yeah. So my f of x was 3 minus a quarter x, and I'm using floating point approximations for a quarter. Notice how I also let it know that this 3, I want everything to be in floating point. So instead of just writing a 3 with no period, I say 3.0 to let the Python know we're going to use precision here. This stuff isn't integers or whole numbers. So I got this. What does that look like? What is the graph of that? It's a line, right? Yeah, it's a line that has negative slope. What's its y-intercept? 3, 1, 2, 3. What's its x-intercept? Who knows, right? But so it's 3 equals a quarter x, so 12. Is that right? So then this line comes down here, blah, blah, blah. We're gonna make this scale crazy. It's like 1, 2, 3, whatever. Let's just make this 12 right here. So then it goes through there, and it comes down like that. The diagonal line, y equals x, you need that for the cobweb. So here's what we expect to happen. We go up to our function, over to the line, down to the function, over to the line. I expect this to narrow in on that point, at least from the picture. So let's take a look. What did it do? Well, let's see. I used an initial value of 1/2. That's way over to the left. And immediately my iteration value, in other words, when you plug, what was my initial? When you plug 1/2 into here, look what you get. You get 3 minus 1/8. That is 3 minus 1/8 right there. So that's my first iterate. The error on the true value of this thing, well, what is the true value of the fixed point? Let's find it. FP true val. Basically, I just have to solve, and we can do this by hand, this equation, set it equal to x. So it's 3 equals 5/4 x. So x is equal to 12/5, which is 2.4. Does that seem right? 2.4? I think so, yeah. And look at where we end up. So this is working, this is good. We got the true, we can do this by hand. We don't need a computer, so that's why it's cool to see what a computer would do with this. So we're headed toward this true value of 2.4. And so what we've got each time is the absolute error in our current approximation right in this middle column. Look at how the error bounces around, but it's always going down. And it doesn't look like it went down here, but you have to remember that's this number times 10 to the negative, is that 5?
That's 5.
Yeah, it looks like 50. Yeah, I guess it would be, if the 5 would be here, but it's 50, so it's just 5. So you're getting the decimal point shifted more and more. But look at the ratio of the error. Does that number look familiar at all? Where's that number coming from in the error ratio? Because it's kind of constant, isn't it? I mean, you know, it's roughly the same thing every single time. What does that number reflect in our problem? Oh yeah, Josephine.
Is it like the 0.25 that was attached to the...
Absolutely, it's the slope of our curve where it intersects that diagonal. But it's always a quarter. So the slope of this line is negative a quarter. M equals negative 0.25. And what we're seeing here is that that seems to somehow relate closely to the error propagation, or the error as we change from time to time. So the error goes down every single time by a quarter on this thing. And you can see, we've got a hella good approximation. Let's tweak that function. Let's take this and turn it into 3 minus x. So change that function, run the program again. easy tweak, right? This is the kind of tweaking I'm saying for assignments. What happened? What's that?
Just makes everything one. There's nips and there's.
It does. What are your iterates doing? You're right. The error never improves, really, on this, right? The error is looking pretty bad. What is happening? Someone tell us with a cobweb diagram. Plot that out. I have to go pee. Plot that out. Look at what happens to 1/2. Make the cobweb. I'm going to make you make cobwebs at some point. Why not do them now before they're required and we can talk about it? I'll be right back. Oh, you're all good. Thank you. Wow, that's a lot of room. That's awesome. Anybody see geometrically what's happening here? We might have to shut this down so we can look at it together. Goes a long route. I know, it's a drag. So let's look at 3 minus x and iterating on that. So first off, does everyone see that it never settles down? The error never diminishes. What is it bouncing between? What is the output, the iteration bouncing between?
2.5 and 2.5.
Yeah, so 0.5 and 2.5, right? Bouncing back and forth. Let's think about why this is happening. Not with that. Maybe with this pen. Cool. So we're going to graph out 3 minus x. It is a beautiful, perfect diagonal with slope equals -1. Remember, the slope on the thing we just saw was in less than 1 in magnitude. And then here's our y equals x, right here. So, and then this is 3 minus x. So here's our fixed point, right here. But we're not getting it. What should our fixed point be? So true fixed point, let's get that. We've got 3 minus x, we're going to set it equal to x. So we set that, right? And so we get 3 equals 2x, x equals 1.5. That's the true fixed point. And let's think about why that is. If I take 3 minus 1.5, what do I get out? 1.5. When I run that back in, it stays the same. So this is my fixed point right here. That's the true value. We're not getting there. We started at, let's label that, that's 1.5. We started way over here, about 1/3 of the way across that distance. And we originally go up to our curve, and then I go straight across to the diagonal, and then I go up or down to the function itself. And it takes me back down here. And because this is a perfect diagonal with this one, I end up actually just looping back to where I started. And I'm seeing that, so I can understand the behavior by making a picture and looking at the cobwebbing process. If you ever, you're like, I don't want to do it by hand, you can go to just search on cobweb GeoGebra. There's a good one there, good cobwebbing app. You can enter your function in and watch it iterate. Does this make sense? Because it's very simple. Yes, Josephine.
So if we chose a different initial point, would it still get stuck?
Well, let's try it. I like that question. What a great freaking question. So what would you like to try?
I don't know.
You give me something weird.
It's too much pressure.
Is that too much pressure?
Yeah.
Just pick any number in the world. What's your favorite number? Make it not pi. Okay, pi it is. No. Okay, I'll pick one for you. So I'll pick a different one. Let's pick a weird one like x equals -1. Because that's not even in this range. So we're going to pick x equals -1. So this is our initial iterate. Then x1 is going to be the function 3 minus x evaluated here. So it's 3 minus -1 equals 4. What's x2 going to be? It's going to be 3 minus, plug that back in, 3 minus 4 is -1, so I'm back again. Yeah, so it doesn't matter. Doesn't matter what I got. And we could probably prove this in general just by run. You could prove it all sorts of ways. Does that sound, okay, cool. I've got one more experiment I'd like you to do. Change the problem to this, 2.0, and then you have to put asterisk x. So 3 minus 2x. That's the thing. Try that, please. Tell me what you see. No, you're fine, you're fine. Nobody needs to scoot in. We're all good. You guys are great. Got lots of room here. If I hurt myself, it's on me. And I'll kind of just run a little experiment up here to see what happens. And you can pick whatever, you can set your initial point to be whatever you want. Oh, I guess I picked pretty good. I actually picked the fixed point. That was not super. That's not what I wanted to see. You can, if you pick it right, you're good to go. So x equals 1 is the fixed point. So let me just go with a half. What the heck? So I'll make x not a half. x1 is 3 minus twice that. Oh, that works. So that's 3 minus 1. That's 2. x2 is 3 minus 2 times 2, that's -1. This is looking grim. x3 is equal to 3 minus -1, so we're at 4. Let's do one more. x4 is equal to 3 minus 4, that's -1. Oh, wow, that's cool. Did you see it loop? Because it looks like it's about to loop, unless I did my math wrong here. It didn't loop. Did I do something wrong here?
You did multiply by 2.
Thank you. Yep. Okay. That's why it was weird. I appreciate you. Thank you. So 2 times -1. Awesome. That's 5, right? Yeah. Okay. Then x4. I was actually shocked by what I was seeing. So I'm glad that it's slightly less shocking. What is happening to the iterate?
It's getting further away from the fixed point.
It's spiraling away. If you were to make a cobweb of this all, so 3 minus 2x, you've got a very steep slope. There's, what is, 6, no, 3 minus 3, right? 3, and then 3. Wait, that can't be. What? 1.5, sorry. 1.5. And then we've got this like this. What you are seeing is this thing spiraling away. So this method doesn't get us an answer. It doesn't converge, is the way to say that. This method diverges on this problem. We would need to do a different method completely. So, and we've got a library of them. All right, let's do one last one. I didn't think we'd do this, but we're definitely doing it. Let's set x naught to 0. So the initial x, I forgot what I called it there. Let's set that to 0.25. Pick any number you want between 0 and 1, except a half, I think, please. And then let's let our function be 4.0 times x times 1 minus x. Probably one of my favorite functions ever in my lifetime. And it relates to the shirt that I brought in, that I said, look at this shirt. Tell me what you see. And then pick a different initial value and tell me what you see. Actually, take the initial value and move it just a little bit. So run this experiment and then make it 0.2500001. Just tweak it a tiny bit, right? Blow on it. A little bit of dust comes onto it. If I look and see what you're doing here. Which one is this?
This is the plus 001.
Oh, okay, cool, cool.
Without it, it's
Oh, it works out real. Oh, wow. Awesome. Wow, that worked out good. I guess 0.25 was, that's cool. Did your 0.25 just stay 0.25? Yeah? No, wait a minute.
It didn't say 0.25.
Oh, what does it do?
Constant at 0.75.
Oh, it goes to a constant at 0.7. Oh, thank you. That's, yes, thank you. So, when you enter this, your sequence goes x naught is it literally this, and then it goes to 0.75? Yeah? And then it's that forever. What happened when you did this one?
It's just 0.25.
It's very messy.
It gets pretty messy, right? There doesn't seem to be any discernible pattern here, because someone tells, so x naught is this, 1, 2, 3, 1. What was x1?
Zero point 640023
0.64.
0023999.
Cool, yeah, cool, that's good. That's good, thank you. And then what was your next one, Cormac?
0.921573.
Does it look like it's repeating or settling down or doing anything? And what's our error doing?
Error is
bouncing out.
all over the place.
Bouncing all over. Is the ratio of error to error settling down? So like in that last right column, is that settling? Doesn't look like it, right? What is going on here? Well, let's look at cobwebs. The answer to understand this is cobwebs and a little bit of understanding about chaos. Because what you're seeing right now is an example of a chaotic system. We took something and we got a very predictable result. You know the butterfly effect? So we just, I don't like stepping on butterflies, but one of you guys did. So one of you guys stepped on a butterfly, really screwed it up. We tried running it again, didn't think it would matter, and it mattered greatly. Yes, ma'am?
When I put in my initial value with the 2.5, then 3 zeros and the 1, I got different numbers. I don't know.
And honestly, that's not, what did you get? I'm curious.
The iterative values for my
Oh, this should have been this, sorry.
Oh wait, I had 2001.
And that's my fault. It's my fault. So I think you probably did the thing I was saying. Cormac did the thing I wrote, but it was still pretty bad, right?
Well, if you have
Kind of, they're-
25001.
Oh, okay.
Initial, it's not that bad.
So what was the next iterate then?
All of my like next iterates are very similar to 0.75, but they're like a little bit over, a little bit under.
Little bit over. Okay, cool. So maybe we're still close enough. Let's do one last tweak. Let's make it a slightly. Maybe it was like a really big bug that we stepped on. So here's a beetle. You heard it crunch. Yuck. Let's try this and see what happens.
251 is the initial value.
2.5. Yes. Thank you. Yeah, I can see why you'd want to clarify.
It goes all over the place.
Does that go all over the place?
Yes.
Okay. Cool. What is the next iterate?
0.751996.
So we're like, oh, okay, so like that, right? So it's kind of close, cool, but what was the next one?
0.745999.
Wow. So like that, 746.
Yeah.
That's not at all, like, it's kind of there. Does it seem like it's settling? Is the error diminishing? And you might need to pull down, the error staying kind of constant, or what is happening? Just going all over?
Stays around 1 and then it just kind of shoots up and then shoots back down. Shoots up.
Cool. So a slight change in initial conditions resulted in unpredictable behavior. That is the definition of chaos, sensitive dependence on initial conditions. And we're seeing it here. So let's talk about what's happening. This is an example of a particular state of what's called the logistic map. And the logistic map says you take an input and you spit out some constant r times x times 1 minus x. So this r is a parameter. And then you could just repeat this. So loop. Take this, that's your new input. Just keep feeding it through. So we're thinking about this cobwebbing process with this as our function. And for us, r was 4 in that last example. So what was that function? It's this. And we're finding the fixed point of it. So find fixed point of this function. And to do that, that means we're going to cobweb. Well, here's y equals x. Always have that diagonal in my cobwebs. And this r, what is this shape? What is that shape? Sorry, you can't see that over there. If I said y equals that, what is the graph? It's a parabola, right? It's a parabola with what x intercepts? 0 and 1. Yeah. So it's a parabola that looks like this. This r in front controls how high it gets. So it's kind of the magnitude of the parabola. So for certain r, the parabola is going to live down here. So this is for small r. I forget where that cutoff is. But if the parabola is under this line, think about how cobwebbing will go. We expect it to head to 0. If the r is small enough. If r gets a little bigger, this parabola intersects the graph. And we get the fixed point. Think about how that happened. As the parabola increased, this intersection started down here and started to move up. And this is actually our fixed point right there. So when we do the iterations, we get, looks like we kind of head there. So let's see, let's try it over here. Kind of end up going there. This is pretty shitty. Like this, like you can't trust these drawings, but this is roughly what's happening. So apparently what happened is we got an R value, we got this thing up here in such a way that wherever we start, we're going to get really unpredictable patterns. So let me show you what I mean with some actual graphic aids here. Okay, so Desmos. Oh no, what did I say? GeoGebra? Cobweb. Oh, yeah, okay. course, you don't know me. Why would you know me? I've only been here for like 20 years. Okay. There we go. Okay, so let's try that again. And I hate the search engine on Brave, the default. So let's just go to Google. Yeah, giving Big Brother all my shit. But Big Brother returns better results for me. Saves, pay my soul for good data. So let's see, so GeoGebra Cobweb. And I always have this interactive to kind of, I think that helps. Oh yeah, there we go. Cool, this is the one I wanted. That's beautiful. Let's see how weird, oh my God, sorry. Go. Okay, so it's going to be a little weird and skewed. We got the idea. So I got to reload that worksheet. Cool, so let's change this to actually, here, I'll kind of show you the cases I was talking about in case it wasn't obvious what was happening. 0.25 times x. Oh, I don't need the weird times there either, do I? X times 1 minus x. And I want my initial value to be between 0 and 1, so that looks good. So now I iterate. And let's blow this up. And you'll be able to watch the iterations. See how it's just cruising down to 0 there? So let's see if we change this, if this will actually keep the iterates and modify them as I change the function. That would be really groovy. So let's say, make this 1.2. And why, what is wrong? Oh, well, yeah, the math's got to be nice too. So I gotta add a param on the end. Cool. Ah, okay, that worked. Close this garbage. Zoom out. Zoom out. There we go. Oh, cool. It automatically changed it for me. So we're still cruising down, but now look where we're headed. We're actually headed toward that fixed point. See how it moved up from 0 up the curve? And let's do that a little bit more. And over on the right, I've got a nice table that's showing the iterates. Let's just do a few more so that table can propagate. Looks like it's kind of converging, doesn't it? To 0.1768-ish, something. Seems like it's converging. And we can see that in the picture. So let's change this number out front one more time. Let's change that to a 2.5. And let's hit enter. And it automatically fixes it. Wow, that was hellish. Oh my God. Okay, well that was pure luck. The initial condition, 0.6, is the fixed point there. So let's see, I think I might be able to move this. Oh, look at that. Yes, yes. Notice how no matter what the initial condition is, we spiral in on that fixed point. Okay, so things are about to get a little weirder. Let's change this. I wish I could just set a parameter here, but let's change this to 3. 3.0, hit enter. Okay, this is what I wanted. Look at the numbers on the right in that table. I don't know if you can see them because of the weird skew this all has. Well, let's actually zoom in here. Look what's happening. So I upped that height of the parabola to 3, and now what's happening is I'm kind of bouncing between two states. It's not settling down to the intersection. It went like this. So this is called a 2 cycle. What we would see over here, and we kind of see it, it's bouncing between 0.69 and 0.64 forever. And it'll kind of just do that forever. Let's up the thing a little bit more. So let's move this to 3.4 out front. And I know something about these values because this is one of my great math loves. So, oh no! Look what happened now. Oh my, that looks terrible. Look at those numbers on the right. No idea. And let's finally, let's look at the last thing that I showed you. 4.0. So this is the situation we found ourselves in, where it's madness. This is a chaotic state. And let's talk about how we got there. So I'm gonna show you with drawings. Maybe I'm not. Maybe I can find somebody to do it for us. So let's see. Google. I want logistic map bifurcation cobweb. Logistic map cobweb. And hopefully this will have a little parameter on it for us. I think I've been to the St. Mary's one. That's pretty disappointing. No, thank you. I want one with a slider. You know who always has sliders? GeoGebra. And there's really something very cool that's about to happen. Yeah, there we go. Okay, cool. So this is the parameter of the height of the parabola. So now watch what happens as I increase it. When it's 0, everything's just dead and not much interest here. But as that parabola creeps up, so does the fixed point. Now the fixed point's at that intersection. And then as I move up, it's kind of just going right to that fixed point, right? And then it's spiraling in. Can you see the spiraling there? And as we increase the height, and you could think of that as a growth rate. This is actually used to model a simple model of population growth. And so what we see is our population eventually settling into an equilibrium state. Then suddenly it changes its qualitative state. I keep changing your little son bitch. Come here. So now it's kind of narrowing in on every time I let go of it, it slides away. It's spiraling down, but then it kind of like approaches this bouncing back and forth between two values. As I increase this even more, you're about to see something, if I can actually, oh yeah, that was it, watch. Okay, look what's happening here. There's 2 states up here and 2 states down here now. So it's kind of like 2 squares that it's bouncing between. And what we see, I got one more map to show you. Okay, let me find this guy. How much time I got? I got 8 minutes. Okay, I swear this is going to be good. Cobweb, logistic map, cobweb, logistic map, explorer. Let's try that. Oh, time domain. Okay, cool. I do want a time plot. Yes, this is the sucker I want. Because on the right, it's showing us the iterates. So what you see here is how they're settling down to this every other state. That's a 2 cycle. As I increase this parameter R, which I guess is this, yeah, 3.5, let's enter that. And do I have to restart the simulation? Yeah. So now look, each of those 2 states split. The top one split into a 2 cycle, the bottom one split into a 2 cycle. Let's up this a little bit more, 3.53, and restart the simulation. So they're moving further apart, 3.6, restart simulation. Look, things are starting to get a little weird. 3.7, restart simulation. Really quite weird. There's a little bit of rhythm in there that you can detect. Let's see, 3.8 here, restart simulation. Kind of looking weird, but you can look at the cobweb and see that it's settling in on some things, because those really heavy bands. But the minute we hit 4, the minute we hit 3.95, some crazy irrational number, let's actually get there. So let's hit 3.95. Things start to get really terrible. And then when I hit 4, we have absolute chaos. So I want to show you a different way to see this. If it will, there we go. Yeah, so that's like pretty much absolute chaos there. So what is happening? What is happening is this. And we can best view this through what's called a bifurcation diagram, which was what my shirt was, but I made it into a tree because I'm like a hippie or something. So, certainly was when I was younger. So let's make a little chart here. This is the R parameter. This is the height of the parabola. And then over here, this is going to be the fixed points that we find. So when R was really small, we only had one fixed point. When R was 0, the fixed point was 0. And then remember how it moved up the parabola? So its x value was increasing. At some critical juncture, at some R value, it split. It bifurcated into a 2 cycle. And the 2 cycles grew further and further apart. And then each of those, at a value that's even closer to that, each of those then split into a 2 cycle, and they grew further apart. But what you can't see in the thing that we did, because it's just not refined enough, is that this splitting occurs faster and faster and forever and ever. So if you say, hey, is there a 2 to some power m cycle in here? Yes, there is. You just have to find the right. No matter how big m is, that number will be in here. That cycle will appear. The forks will have that many branches on them. At R sub chaos, suddenly, this cascade of bifurcations, and that's a technical term, we see cascading 2 cycles, all of a sudden break into a chaotic zone. And there's no fixed points in here. So there's this region in here that's pure chaos, and nothing ever settles, no matter what your initial conditions are. And then it starts up again. It'll have like it'll calm down a little bit, and then do some more, and then break into chaos again. So I want to show you really quick, we've got 3 minutes. This is a fractal. It is a picture with infinite, just like the Newton thing we looked at last week, or Tuesday, whenever the hell that was, Monday. This is the same thing. It's got infinite depth and infinite structure to it. So let's just take a quick look at a really beautiful Zoom movie. So, well, and this will be the end of the day. And then you can just go on and your brain will be good and primed. So logistic bifurcation diagram Zoom. Oh look, I've searched for it like 1,000 times. So this is a pretty good one. Let me see the cameras. Okay. I want to zoom this up. I want this to be something that we end our week with beautifully. All right. So this is way back because apparently I was watching this like for recreation, like a freak. So you're going to see that bifurcation diagram of fixed point states. And we're going to zoom in on it. See, single, 2 cycle, 4 cycle, 8 cycle. But look at how, first off, there's these beautiful dark patches that appear in here. And then within the chaotic regions themselves, if you zoom in on the right spot, the whole diagram appears again, over and over and over. So infinite self-similarity is a hallmark of fractals. It's not always there. But if it occurs, it's probably a fractal structure. I finally learned what those dark lines were last year, and I've totally forgot because I didn't learn it. But I understood it for a minute, why those dark, beautiful curves appear. Now what we're seeing here is we're getting to the limit of the machine precision. So it's starting to come apart because we're so close in, the numbers are so small, it can't even do it. Now hold on, because we're going to pull back out at 1,000 miles an hour. So there we are at 1.8 times 10 to the negative 9th as our precision, as our zoom. I guess that's the zoom window, how wide it is. It's almost done. It's only a couple minutes. Just give it a sec. Do you recognize the tree that I had on my shirt? Yeah, just turned sideways. Drew some goofy branches on it. And there is a hidden secret left side that we don't talk about normally, but there's a secret side on the others. So, so those T-shirts are available at Divergence. Never mind. They actually are available, but don't go buy one. Thanks, everybody. Happy end of week 3. Keep an eye out. I'll let you know when I post an assignment. Yeah, it is. Yay. Absolutely. Yay. Almost a quarter of the way through. No, let's go. I was just saying hi. Sorry. I'll leave that out of your way. How you feeling? Feeling a little